Without further delay, let me start my talk on quantum information. Actually, it's quantum algorithms, I think. But the idea is that we do computation with digital circuits, with classical circuits. And as someone pointed out, I think it was Professor Scherlicker, that after circuits become less than a certain size, the quantum effects start overwhelming the classical effects. So for a long time, people were able to treat them like noise and design circuits around them. But then luminaries like Feynman pointed out that why not take advantage of these effects to design circuits that will do your computation, rather than just treat them like noise. So this uncertainty principle, which used to generate noise, is something that we potentially can use to our advantage, and that is quantum computation. Algorithms or techniques that take advantage of the uncertainty principle to do things faster than they would otherwise be possible constitute quantum algorithms. Still remains to be proved, but the way things are going, this might very well be true. I will talk a little bit about the D-wave publicity which has recently come about. It is very interesting, although I should say right in the beginning that it is not something that has been peer-reviewed. So if it comes to naught, or if nothing comes out of it, quantum computing is still very much alive. So let us start by talking about classical computation, things we know and love. What is classical computation? The thing that classical computers can do, I'm talking about digital computation. Analog computation is potentially, I was about to say more powerful, but at least as powerful as digital computation, and very little is known about quantum analog computation. But what classical computers can do very well is compute digital functions, Boolean functions. So given a Boolean function like A, B, C, D, we can design a circuit that will compute it for any inputs A, B, C, or D. And this Boolean function can be of arbitrary complexity. And classical digital circuits can be designed that will compute it. And that is pretty much all classical digital circuits can do, right? Compute Boolean functions much more very efficiently. Combinations of Boolean functions, variables and their complements too. So for example, a circuit like this will compute the function that I just described. And the interesting part is that it will compute it for any inputs. Over here, I can have any inputs and it will compute the output. And the reason this thing has become so efficient is that they can be implemented with semiconductor electronics. Each state is encoded as a particular state of 10 to the power of 21 electrons or so. And the dynamics of it is such that it maps very, very closely into the computation of Boolean functions. So this is a thing that has generated the digital revolution in the last 20 years. This ability to use semiconductor electronics to compute these Boolean functions. Suppose instead of 10 to the power of 21 electrons, we were to go to 10 to the power of 20 electrons. Well, things would become smaller. Our circuits would become smaller, more efficient, less power dissipative. And that is what the VLSI revolution has been all about. If we were to go to 10 to the power of 10 electrons, then you come to nanotechnology and the nano revolution. And if we were to go to 100 electrons, then you come to DNA computing. But the mechanics stays pretty much the same in terms of the fact that all that is happening is the computation of classical Boolean functions very, very efficiently. But if we were to go from 100 electrons to 1 electron, then things change drastically. All kinds of quantum effects come into play. All the circuits that we had before break down and do not work. And what happens? We really don't know. Actually, it turns out we do know what happens. Feynman, when he got interested in this area, he gave a talk at Bell Labs in 1986, which I was privileged to being able to attend. And the main point he was making in that talk was that when circuits become small and quantum effects predominate, you will still be able to do computation. Things would have to be designed differently, but the digital gates we know today, we would still be able to implement them. The analogy he gave, I still remember, that when aircraft were being designed in the 40s, supersonic effects were proving to be very, very dissipative, and people had theories that aircraft would never be able to fly faster than the speed of sound. Just like the speed of light is a limit, there were theories that the speed of sound would be a limit for aircraft. But then engineers, through intelligent design, were able to design their way around that, because that was not really a limit. But what was the fact was that in the new regime, the principles of design were very, very different. So the Concords are designed very differently from the other 747s. Similarly, the quantum circuits that would be designed to be able to implement microprocessors would have to be very different, but they still could be designed. And that was the state of the art when Feynman was there in 87. So what is quantum computation, or how would they be designed? This is something which I told you and you know about. These are the circuits that come about when you have quantum effects predominating. You still have gates. They're different gates. You have gates which I call H. But what is really, really different is that instead of having one number over here, you have combinations of numbers. This is called a superposition of states. That it is somehow in both states at the same time. It is not probability that it will be in each state with half probability, but it is somehow in both states at the same time. And what is really different is that when you have combinations of inputs, then you have it in combinations of states. And this is called entanglement. And this is something where quantum mechanics is really at its most mysterious. It doesn't take too much, just a circuit like this, to be able to illustrate quantum phenomena which are very mind-boggling. The quantum computation, as I mentioned, uses two-state systems. In classical computation, every step is deterministic. I already told you, over here, every step is non-deterministic. But the real power of quantum computation is not that it enables you to function when the circuits get smaller and smaller. That it of course does. But the real power of quantum computation, which Feynman never realized, was that you can do things which are not possible classically. That because things are in a combination of states at the same time, you can take advantage of that to do certain things much faster than would otherwise be possible. And this is what today's talk is about. So what is quantum computing? You start with a state that is easy to prepare, like all electrons in the zero state, which is a classical state. And then just like you do a digital computation, you apply a sequence of operations which you can analytically show will drive the system to a state which will give you the answer to a complicated problem. Just it's the same as in digital computation, except the intermediate states will not be 0 and 1 states. There will be combinations, superpositions of state. And at the end, you do a measurement. So no different from what is happening digitally. So for example, one reason why the D-wave demonstration looks pretty similar to what a classical digital circuit would be. From outside, it's just the same. You give it a certain input, and at the output, you get a certain output. But what goes on inside is very different. And the reason the quantum, it's taking so much effort to be able to build these quantum circuits is that quantum circuits are very different from what we are used to classically. I mean, all the circuits, all the devices that we know and love, like the laser and the transistor, make use of quantum mechanics. But at their core, there is this averaging over multiple quantum systems that has been performed. While in these quantum computers, you want to be able to do it at a single quantum state level. So far there are no devices known that will be able to do things at the single quantum state level, except which are now being discovered. Power of what are the quantum gates that we can implement? First of all, I told you that we can implement all the gates we can do classically. Plus, we can do some that are not possible classically. And what are those that we can't do classically? Any quantum operation is a rotation of the state vector in multidimensional space. But the operations that can be done easily are rotations in two-dimensional space, or 1 or 2-dimensional space. Just like classical computation, we can compute any Boolean function efficiently. But the Boolean functions that can be technologically computed efficiently are those that can be done with 2 inputs, 1 or 2 inputs at a time. So the idea is to be able to build up powerful sequences of computation that you can do just by 1 or 2 inputs at a time. Let me give you an example of a quantum mechanical gate. One thing that I should emphasize is that these are rotation operations. People who have seen matrix algebra would be able to recognize these as unitary transformations. So the transformations that can be done over here are 1 or 2 dimensional rotations, or rotations in 1 or 2 dimensions. These 1 or 2 dimensions can be pretty complicated, but they have to be 1 or 2 dimensions at a time. So a basic gate is this Hadamard transformation. What does this gate do? First of all, just like binary digital systems, you can build 2 to the n state systems, can be built out of n 2-state systems, just like classical binary systems. And in this Hadamard transform, each of the n qubits is independently rotated by a certain amount. So this you have this these n-state systems coming in, and each of these states is rotated by a certain amount, and you get this output which is completely different from the input. So how is this, each of these rotated? By this transformation. It is in 2-dimensional space. And what happens to any of the state basis vectors? If you start with 1, 0, you get 1, 1. And if you start with 0, 1, you get 1 minus 1. Actually, it turns out that the probabilities are proportional to the squares of these amplitudes. So if you were to do a measurement of the basis vector right after applying this transformation, you would get exactly the same result. So it is completely randomizing as far as the basis vectors are concerned. But then if you apply it twice, then since the inverse of this is the same as this transformation, you get the same thing back. So this is, if you were to look at just at the state vectors, this is a very simple demonstration of quantum mysteriousness. That you apply one transformation, you completely randomize the state, and you apply a second transformation, and you get the state back. So if you ever want to exhibit magic tricks, and you have this quantum gate, this is a simple way to amuse children. But turns out you can do other things, more interesting things with this too than amusing children. And they are what we call quantum algorithms. The first and perhaps the most important quantum algorithm discovered was that for factorization. And the other, what am I doing for time?
No problem.
How much time have I spent?
Half an hour.
I've spent half an hour.
No, you have got another.
Okay. And the other algorithm which I'm going to talk about a little more about today is that for searching unsorted structures. The classical complexity of the factorization problem is n to the 1/3. N is the number to be factored, and the simplest classical algorithm for factorization is to start with 1 and go looking, try out every number until you come to one that divides the number. And if you don't come to any number, then that means that it is prime. I'll talk about the searching problem also a little more, in a little while. But notice one thing, that we have to search n items. And classically, no matter how smart you are or how many good algorithms you try, you could not do it faster than n steps, because there are n items to be searched, right? And they are random. So if you leave out any items, you could potentially be leaving out the answer to your problem. So this is something which is something that you really need quantum mechanics to do. Factorization, so far no one has found a better algorithm than this n to the 1/3, while Peter Shor found a log n algorithm. But it's still possible that some might exist. Okay, let me, before I get too much into factorization, let me talk about what the factorization problem is. If someone were to give you these two numbers, 103 and 209, and ask you to multiply them and give you a paper and pencil, you could perhaps come up with the answer in about a minute. That's because an efficient algorithm for multiplication is known. But if someone were to give you this number and ask you to factor it, it should be not easy. Easy with quantum. It would take you about half an hour to do this. That's because no classical algorithm, no efficient classical algorithm is known. And people have tried very hard to find efficient algorithms for this, so much so that the complexity of coding systems is based on the difficulty of this problem. So if someone were to find inefficient algorithms, all the secret transmissions among banks and security agencies and spies would suddenly become public information. So when Peter Shor came up with an efficient algorithm for factorization, which made this problem as easy as that for multiplication, all the security agencies sat up and took notice. And that is one thing that started this quantum computing revolution. Okay, the second algorithm is that for searching, unsorted structures. The problem is this, that you are given a dictionary with 1,000,000 words, and there is this crossword puzzle to be solved. If you were given this database on a classical computer, you would be very, very hard pressed to write a program that took less than 500,000 steps. That's because the database is just not sorted according to the 3rd, 5th, and 6th letters of the words. But if you were given this database on a quantum computer, then you could very easily write a program that took just 1,000 steps. And that is by using the uncertainty principle, that the quantum system is naturally in multiple states at the same time, and instead of using that to your disadvantage, we use it to our advantage to be able to search multiple things at the same time. And you'd get this answer piranha, instead of 500,000 steps, you'd get it in 1,000 steps. How does one do this? The easiest way, or the most physics oriented way to think of it, is to think of the Schrodinger's equation. That what this does is it evolves the system in a certain way such that it is a combination of random transitions plus phase rotations. This del psi by del t, when you have I multiplied by a real number times the amplitude, it is a phase rotation, while this thing is a random transition. So it is a combination of random transitions plus phase rotations. And what is happening is that the phase rotations are equivalent to a potential. This is something Schrodinger realized a long time ago. And so what my contribution was to implement the same thing digitally, that these random transitions were simulated a certain way, and these phase rotations were simulated a certain way. And the net result was that just as in this Schrodinger's equation, everything gravitates towards the points of lowest potential. Similarly, everything will gravitate towards the points towards the points of the database whose phase is being rotated. And it turns out that it took square root of n steps to do this. This is not at all obvious why it should take square root of n or n to the 1/4. One just needs to do the calculations and find out. Turned out I was looking for an exponential improvement. So when I found a square root of n, I lost interest in it because it would not solve the NP-complete problems, which was what I was interested in. But after a while, when I could not make any more headway, I went and showed this to Peter Shor, and he said even the square root of n might be of interest. So what is the algorithm? Roughly it is this, that you put the system into all the states at the same time. This is something we know right from the uncertainty principle we can do. Quantum systems can be in multiple states at the same time. But now if we were to do measurement, we'd only get the answer with a 1 by n probability. This aha person would say that he has the right answer, and in all other cases it would collapse into the wrong state. Instead, what we do in the search algorithm is, through a series of quantum mechanical operations, drive the system so that it increases the probability of this aha state. So the quantum mechanical search is a sequence of operations that drives the system from here to here. And it turns out it takes square root of n steps to drive it from here to here. And now if you observe the system, the probability of getting the right answer is very high. I think I have landed up with an older version of the talk, but let me go on. The thing to realize is that what is happening in quantum and classical search is very different. Just like the principles of airplane design were very different in the two domains. Over here, what is happening is, classically, it is the probability in the non-target states or non-desired states that is being gradually reduced through attrition. While over here, in the quantum search, the amplitude in the target state is being gradually built up. And this should have actually come after the amplitude amplification, but it is based on this randomizing operation, which puts the system into multiple states at the same time, and then applies the potential at each step. This is the potential at each step. So the idea is that we should be able to selectively invert any of the states we want. Classically, we can check whether any of the states we desire or which is a candidate state is a right state or no. Similarly, quantum mechanically, we can apply a phase rotation to any state we want. This is another transformation that can be implemented quantum mechanically. That what it does is it changes the amplitude in the target state without changing the probability. So in itself, it is completely useless because it is not going to increase the probability of success. But what we can do is after this apply other operations which will depend on this and will take advantage of the fact that the phase of the target state has been rotated. And this is the circuit that does the phase rotation. The idea is that if you have a black box that can compute this function f of x bar, that given an x bar, it can tell you whether or not the function was 1 at a particular point. You can put a small amount of hardware around this, which will, instead of telling you whether it was 1 or no, invert the phase of the target state and leave all others unaltered. It is not realistic to go into how this circuit works. I mean, it is like people who, if you have not seen a microprocessor before, it is not something that you want to be explained, you want to hear about in a short period of time, although the principles are very easy. So it is that technique. Basically, it is now we have to carry out the analysis of a quantum type circuit. And quantum circuits are analyzed state by state. So one of the things that this quantum search is based on is something called a randomization. And the way the randomization is implemented is this called inversion about average operation. And an inversion about average is something that can be easily done quantum mechanically. And what is an inversion about average? These things are the possible states. There are 8 possible states. These bars are the amplitudes in the 8 possible states. And the inversion about average keeps the amplitudes which were at the average the same, which were below the average, like the 6. It brings them as much above the average as they were below the average to start out with. And same goes for things that were above the average. So if you look at it, it completely seems to randomize the state completely. And this is something that can be implemented quantum mechanically. And quantum search algorithm is based on a combination of this inversion about average and selective inversion. So forget about this, this portion, top portion, just look at this last portion. You start out with everything equal to the average. Since there are n states, the amplitude in each state is 1 by square root of n. And then you invert the state, which was the target state. If this was k by square root of n, it was minus k by square root of n. The average one can show stays pretty close to 1 by square root of n. It falls by a little bit. So this guy is minus k by square root of n, average is 1 by square root of n, so he's k plus 1 by square root of n below the average. So if you perform an inversion about average, these guys are going to fall a little bit, and he's going to go to k plus 2 by square root of n. And then if you invert it, it will become minus k plus 2 by square root of n, and then k plus 4 by square root of n. So it increases by 2 by square root of n at each time, at each step. So in square root of n iterations of this inversion about average and selective inversions, it will become all the amplitude gets driven into this state, and then if you do a measurement, then you get the right answer with a high probability. So this is all the quantum search algorithm is. The encode the n states with log n qubits. So what does all this mean? That if we are given this block, which can calculate the function of f of x, and you want the particular sequence of inputs at which this f of x evaluates to 1. We know it evaluates to 1 at only one combination of the inputs. Everywhere else it is 0. Classically, if you were to be allowed to hook up a small amount of hardware around this, you would need n steps to be able to find this combination of inputs at which it evaluated to 1. Quantum mechanically, we can do it in square root of n steps. Quantum mechanically means if this box were to be able to take in superpositions as inputs and put out superpositions as outputs. If this box were that kind of box, which we know also does exist in nature and can be designed in principle, then we can do it in square root of n steps. Another interesting result was that we could not do it better than square root of n steps, which was quite surprising. A year after this quantum search algorithm came out, it was realized that we could not do better than this quantum search. But the area which was of which proved to be of much more fruitful was applying this algorithm to other problems, because it was something that could be adapted very easily. And that was the idea that this could be used in something called amplitude amplification. That the search algorithm was only one algorithm in a whole class of algorithms. And that result was that if you wanted to drive any system from a source state to a target state, you could apply this sequence of operations which would drive you there quadratically faster than you would be able to go classically. And just like all other fields, over here also it is more convenient to think in terms of pictures. And the picture that emerged of the quantum search algorithm was a rotation. This whole algorithm is a rotation in only two-dimensional space, from the source to the target space. All the other dimensions cancel out. So this sequence of operations rotates slowly, this target vector slowly from the source to the target state. Okay, this I already went through. That not only is it finding applications in a number of areas of computer science, there is also this intriguing application to biology which Apurva Patel has recently realized. That biological systems use this form of encoding. DNA has this, computer systems always use binary encoding, and the reason for that is well understood. But for biological systems, it is not well understood why they use encoding of 4 bases. DNA is an encoding of 4 bases, 4 base pairs. And amino acids, there are 20 amino acids for each base pair. What Apurva Patel recently noticed was that quantum searching is particularly efficient in searching out of 4. It needs exactly 1 query. And searching out of 20, it needs exactly 3 queries. So this could provide an explanation for why this nature has chosen to encode this biological systems in this particular. I should briefly mention one of the most pressing problems in quantum computing is this error correction. Recently, I saw a design for a quantum computer. This was a paper design, and I think 99.999% of its effort was being spent on error correction. And the computation was the 0.0001%, just piggybacking on top of that. And the reason error correction is so difficult is that we can't measure the quantum system without affecting the computation. Classically, you can measure it and then at each step correct the errors and then go on. Over here, you have to do things differently. But Peter Shor and others realized that there were ways of correcting errors quantum mechanically too. But the challenge is that you need the error rate to be very small, of the order of 10 to the power of -4. This D-wave systems has some intriguing ideas which I'll briefly mention. So the implementation of quantum systems is probably still a few decades away. The reason is that quantum systems are very delicate and have to be almost completely isolated, at least the way we understand them now, because you need to operate at individual quantum states and we still don't know how to do that. Is there a way to do that which will not require such complete isolation? Probably not, but there is a small chance that someday someone might come up with an idea which might change the whole field. And these are a couple of implementation schemes. There are a number of implementation schemes. There's a lot of excitement in the field. People are trying out dozens and dozens of schemes and making progress experimentally faster than anyone thought. So it's possible that quantum computers might be on our desks before we have a chance to figure out what to do with them. Because quantum mechanically, the algorithms have not made as much progress as the implementation has made. A decade ago, there were 2 algorithms known, and still there are just 2 algorithms known. Let me mention something about this D-wave system. There was a lot of excitement because they claimed to have a 16-qubit quantum computer, which they claimed would be scalable to 1,000 qubits by 2008. But it has not been peer-reviewed. So it is not something that we can comment on. And it is something like what happened in cold fusion. Some people went direct to the journalists and the press and made an announcement. So the quantum computing community is still not convinced about it. But just the fact that such a thing can happen indicates that there is a lot of scope for new ideas which people have not even thought about. Let me mention something about quantum communication. What I've spoken about is quantum computing. There are a number of allied fields. Quantum cryptography is something that is close to being implemented. Teleportation is, I think it was Charlie Bennett who said that quantum cryptography is the closest to practical realization. It is almost there in the market. Teleportation is the most counterintuitive, but computation is the one with the most potential, which is coming up now.
Professor Grover would like to have some questions.
Yeah, about reducing probability over several steps to get a high probability for the target state. I mean, I don't understand why the process needs to end, in the sense that it is rotating the vector by some amount for every application. It can sort of go on forever, right?
Forever. You want it to end, right? You want.
No, I know you want it to end. What I mean is that can you have more number of steps and increase the probability further of getting the target state as the measurement.
I mean, after square root of n, you come to 1.
Oh, you come to 1.
You come to 1. Yes.
No, because there was something about it being probabilistic in the sense that you increase the probability of the target state, but you can always make it 1 for all kinds of algorithms, or?
There are limitations that suppose you don't know the target state that well. But if you know the target state and it is a well-defined problem, you can always bring it to 1.
Regarding your algorithm, that inversion about mean, when you thought about that operator, what made you to develop, to bring up that operator? Or what inspired you
to look
when you were working on your search algorithm?
Okay. Before I answer that question, let me just talk a little bit more about this analog circuits. Because in analog circuits, even classical analog circuits, so many unpredictable things happen that one needs to think about them. So one would expect that quantum analog circuits, there would be a lot of possibilities for exploration, potential for exploration, especially when you have things like differential amplifiers and other things. So the other question was what prompted one to look into inversion about mean. Actually, I was just implementing Schrodinger's equation. That was the only thing about quantum mechanics I remembered. I mean, I had taken a graduate course a long time ago in graduate school. So the only thing of quantum mechanics I remembered was that Schrodinger's equation was equivalent to a rotation in phase space. So that's what I tried, rotating the phase and then figuring out a way of randomizing it quantum mechanically. And this inversion about average took a little bit of doing to do. I mean, I had to talk to Peter Shor and learn some quantum computing for that.
See, for different technologies for implementation, quantum gates or these transforms, I mean, is it that different technologies can more easily implement different gates, or all technologies can implement the same kinds of gates easily?
No. There are different technologies can implement different gates.
In which case then, depending on the technology used, you would develop different algorithms for the same problem?
That is one of the things that is happening, that one doesn't know which technology is going to dominate, and there are slightly different variants of the algorithms for different technologies. What is happening is that, for example, optics, one can implement 1-qubit gates very easily, right? It's easy to shift the phase of an optical wave, while it's very difficult to get optical waves to interact. Solid state, it's sometimes exactly the opposite. I mean, solids are so close that they interact very easily, but the phase shift is hard. So one figures out a way of doing the phase shift using, I mean, what one always does is bring about a set of operations using the technologies so that one can implement a few core gates. And once you have those few core gates, then you can implement anything you want to. Remains to be seen. But the thing is that it is a very simple algorithm. So it adapts much more easily than algorithms that need a lot of steps.